All right, so we've kind of introduced this concept. We did kind of a generic version of it that sort of was based off the original kind of generic version of the chain rule, but let's actually see, like, in practice, what are we really going to be working with? So we'll start with an integral. What I'm going to start with is here. So let's do the integral of 3x times the quantity, 4x squared minus 5, and that whole thing is raised to the 5 dx. This is something where technically we could do this without doing a substitution. We did some examples earlier, right? If you had sort of a polynomial in parentheses and it was sort of raised to a power, we sort of said that you could actually just multiply everything out and just sort of FOIL it and expand it. Now, I said that when the power on the outside was just something squared, right? If something is squared and you expand it, it's not really a big deal. This is raised to the 5. It could be done, but right, you're going to spend whatever, 5 minutes just doing all the multiplication to actually expand that out before you actually have like started doing any calculus. It's probably going to be faster to sort of do this substitution instead, and then try to sort of use that to your advantage. So what we want to do, what we want to do is pick a good U. And what I'll say here is the way this works is you really have kind of one, for the most part, kind of one candidate for U that's going to make everything fit together. If you end up picking the wrong U, which can happen, the worst case scenario is it just kind of doesn't work. It'll just sort of fall apart halfway through. That's fine. I mean, you're going to make mistakes. That's part of the learning process. You can screw stuff up, and if you didn't, well, you're actually probably not getting the most out of it as you should. So those screw ups are fine. If that happens, you just kind of need to reboot, go back to the beginning, and try something else as your U. The whole thing here, right, depends on kind of this initial first step. What do we want to pick as our U? So the things that I wrote down in the last video include anything in parentheses, anything under a root, any powers on an e variable, or anything that's inside a trig function. The inner stuff in the trig function, in some sense, would kind of be in parentheses. So the parentheses there is kind of going to be a giveaway in any of those cases. No trig here, no e's, but we definitely have a parentheses, right? So this is 4x squared minus 5 raised to the 5. So what I want to pick is the stuff that's in the parentheses. So what I want to pick is just this 4x squared minus 5. So let's let U equal 4x squared minus 5. And honestly, we can just do that, right? We can just sort of, if we're going to just make up new variables, we can have them stand in for any piece of this we want. I could let W equal 3x. I could let Z equal 5. And then this is 4x squared minus Z raised to the Z. Now, those things are just random. They don't really help us or really do anything or simplify this in any way. So I wouldn't recommend it, just subbing in random things and just seeing what happens. That's kind of just chaotic and isn't really going to help. But if we sort of pick just the right one, then we can do this. So I want to pick whatever's inside my parentheses here. So this is 4x squared minus 5. Okay, so let's let U equal that. The second step then is take the derivative, right? So take the derivative. So in our notation, right, that's going to mean find du over dx, right? Du over dx just means the derivative of U with respect to x, right? So that's going to mean du dx. So that's right, like take the derivative, whatever I just labeled. And this is a relatively simple piece, right? This just individually, it just is a nice power rule, right? 2 times 4 is 8, x to the 1, right? Minus 5, the derivative of the 5 is going to be 0. So the setup here is du over dx equals 8x. And what I'm going to suggest here is, again, we sort of said technically, this is not officially a fraction. But what I'm going to suggest is do a quick little cross multiply. I was about to do this in the last video, but then I paused. cross multiply, right? And so actually bring the dx over. So what we're going to get here is that du is equal to, right, 8x times dx. And from there, what I'm going to do is actually solve for the dx. So I'm doing a cross multiply, and then I'm going to divide both sides by this 8x. So my end result here is, right, dx equals du divide by 8x, where, is it showing up? Yeah. U equals 4x squared minus 5. So this is called U-Substitution, right? This is the substitution, right? You're sort of picking these other values, and then you're going to substitute them back into our original integral, right? You're going to plug this stuff back into here. And you're going to sub two things in. And this is where it gets a little bit different than that generic version from the last one. Because the way we kind of do the substitution, and in theory there are a couple different ways you can do this, but it's all the same kind of basic concept. So what I'm going to do is say, okay, I'm going to sub in 3x. I can't really solve for, right? 3x is 3x. The piece under my parentheses, right? So this guy raised to the 5th. The whole starting point here is that that's going to be u. That's my U-Substitution. That's what I picked to be u. And then the part that's going to make all of this come together, right? It's not enough to just pick this u, because then I start getting, right, x's and u's, and this is dx, but if I'm trying to get u, I need it to be du, and, right? Things are sort of coming apart. So what I like to do is just say, okay, well, what I have in the original is a dx. So what I'm going to do is replace it with what I sort of rearranged and solved for here when I did this derivative. So dx would be du divided by 8x. So I'm going to take that and sub that in also. That is in blue. So then that ends up kind of looking like du over 8x. Now, this is kind of messy. This is sort of half and half. This is like a little bit of each, right? So this is like, there are u's, there are x's, there are sort of all sorts of things falling all over the place. However, one of the things that we should notice, right, is here and here, right? Those two x's, one is sort of on top and one is on the bottom. I could actually kind of bring them over top of each other. So if I kind of rearrange that, it maybe looks something like this. And so what happens here is these x's are going to cancel each other out. I'm actually able to sort of cancel whatever the leftover was in my original integral, right? This more complex thing where I have obviously the piece here in the parentheses. I also have this leftover stuff on the outside, this 3x. So when I do this, I get this x on the bottom. I can set it up and I can cancel these guys out. So that's kind of the key to making this work. And then 3 over 8, this is just really, you know, these are just sort of generic coefficients. I don't really need them as a part of this problem. I can sort of just bring them to the outside and then focus on all the rest of the pieces here. So what I'm ending up with in this case, right, I kind of started with something complicated. We have, you know, u here. We subbed in for the dx. We subbed in for our parentheses, subbed in for the u. This guy's over 8x, right? Kind of bring these 3x and the 8x together because the x's cancel. 3 over 8 is just a generic fraction. We can just work with that and it's fine. And the calculus here, right, what I'm really left with is the integral of u to the 5 du. This is just regular power rule stuff. This is just straight power rule, where the variable and the sort of d value here match. right? So this is power rule. And I only have u's in this case. So I've done a full substitution from x's to u's, and now I can just do a power rule. That means, right, that would be u to the 6, right, plus c. I have this, u to the 6 over 6, right, add 1 and then divide, times this 3/8 out front. So what happens when I'm going to clean this up is I can essentially say, okay, well, 3 and 6, that's like 2. So this is what, like 1 over 16. U to the 6 plus c, which then is 1 over 16. So what I want to do here in the end is go all the way back to the beginning and say I want my final answer to be back in terms of my x values. So I'm going to go all the way back and say, well, what was the u here in the original? The u I picked at the very beginning was 4x squared minus 5. So I'm going to sub that back in. 4x squared minus 5. The new power here is 6. And then this is just an indefinite. This is just finding an antiderivative. So then that whole thing is raised to the 6 and plus c. That took a minute. In theory, that's one of the simpler ones. Part of that is just me really explaining the process and sort of taking time to go through it. Let's just take another minute. I just said, essentially saying this is really long, and then my immediate follow-up is, let's talk about it longer. Let's just recap a little bit what we did. So the original, right, 3x in parentheses 4x squared minus 5 raised to the 5th with respect to x. The idea here to get this started, right, it's not really something that we can just naturally do in one step. It's not something, we could do an expansion, but again, it would really, really expand a lot, and that would take a lot of time. Not the best. So I don't want to do that. So I want to try this u substitution. So pick a good u. One of the things it said was pick something in your parentheses, right? So let's do 4x squared minus 5. So let the u equal that. Take the derivative of your u. So du dx is our derivative here. That would be, if this is our g, the derivative, right, would be our g prime. So that's 2 times 4 is 8x. So 8x is the derivative. A quick little kind of cross multiply, rearrange, kind of cross multiply and then divide. Essentially what I'm doing is I'm solving for the dx here. That's kind of what I'm solving for, because I'm doing a substitution for the u, and I'm going to do a substitution for the dx that's here, right? This to this was my sort of secondary substitution. Dx turns out to be du over this derivative. That pattern will always be the same, so that's nice at least, right? Dx is du over the 8x. If I plug both of those things in, so plug the u in here and I sub in the du over the 8x, what happens is, this inconsistency between the x here and the u here, the x gets canceled out by what I brought over and carried through with my sort of derivative, right? It's this sort of leftovers from the derivative. This is essentially the g prime, right, from your chain rule. So if you bring this over, it actually cleans up your integral. The x's cancel out. We have some extra numbers here, but extra numbers, we'll just sort of bring them out front, and they're not going to bother us at all. We can do extra numbers all day long. So 3 over 8 comes out front. Then this is the integral u to the 5. Power rule on that, right? So now that it's u to the 5, and then the integral is respect to u, right? So it's u to the 5, and this is du. 5 plus 1 is 6, right? Divide by 6. A little cleanup, 3 and 6 would leave this at 2. 2 and 8 would be 16. 1 over 16, u to the 6 plus c. Back in, right? That was the original u. So my final version, 1 over 16, quantity 4x squared minus 5 raised to the 6. And then the whole thing is plus c. So that's what we're dealing with. We're obviously going to run a few more examples. There's as always, a number of different setups. So we'll run a few more examples to try to get comfortable and get this technique down.